Everyone. This is Steve Smith, Director of the NOAA's Virtual Lab, and welcome to our May edition of the VLab Forum, where we present, we have presenters on topics related to research to operations relevant to National Weather Service primarily. Today, we're very privileged and happy to have Mike Pavolonis from NESDA STAR, who will be giving us a talk on ProbSevere, a new tool for NWS severe weather warning operations. The ProbSevere is topping the Weather Service R2O charts lately. It's a very exciting project that's getting a lot of positive buzz both within Weather Service field offices, the regions, and now headquarters. The ProbSevere is being considered for operational transition to Weather Service operations in FY18 and will be discussed next week at the Weather Service Annual Operating Plan meeting. So, per usual, our structure for the VLab Forum is to hear about 30 minutes or so of content, in this case from Mike, followed up by Q&A. I remind everyone that the sessions are recorded, and John Chattel will be uploading the recording to the VLab Forum website shortly at the conclusion of the session. Also, we ask that for the question and answer that you use the raise your hand feature of the GoToWebinar. If you'd like to ask a question directly to Mike, we will unmute you and let you do that. Or you can also use the chat feature to type in a question, in which case John Chattel will read it out loud and then Mike will respond. So without further ado, I will hand the presentation over to Mike. You there, Mike?
I am, Steve. Thank you for the introduction. Hopefully the voice is still coming through loud and clear.
It is. It is.
Good, great. And so ProbSevere, which is short for probability of severe, you know, I want to give sort of an overview here and provide a little bit of the motivation of where we were coming from on this, and give you some insight into some of the new developments we've been working on that we're excited about. Of course, this is a major team effort. I'm stationed at the University of Wisconsin at the Cooperative Institute for Meteorological Satellite Studies, where John Centennial, Justin Siegloff have been critical for the development of ProbSevere, and we've also been collaborating with Dan Lindsay out in Fort Collins, and Chad Gravel, who's a satellite liaison stationed at the Aviation Weather Center. So first, sort of overarching motivation for this. You know, we are very much in the era of big data, where data volumes are growing rapidly, in particular from, you know, space-based data volumes, but non-space-based as well. Just take, for instance, the difference in daily data volume between GOES 16 and GOES 13. It's about 2 orders of magnitude different, with GOES 16 being much larger, of course. So there's never been, I think, a greater need to develop sort of big data methods to try to transform these large volumes of data into information. That being said, I don't view big data, especially in regards to National Weather Service operations, as automating final decision making. I don't view it that way. Again, I view it more as taking very large volumes of data and transforming them into actionable information that can improve the efficiency and effectiveness of final decision making, but not automate the final decision. So for instance, with ProbSevere, you know, we take these different data sources and, you know, we come up with information relevant to ranking whether or not a storm is likely to produce severe weather, but it's the forecaster that still makes that decision as to whether or not to issue a warning. So with all of that in mind, here's the synopsis of what ProbSevere is. So what we do is we take high-resolution NWP data from the Rapid Refresh model, geostationary satellite data from the GOES constellation, and MRMS radar products, along with total lightning from the ground-based Earth networks, We put them together in a statistical framework called a Bayesian classifier, and we come up with a probability that a developing thunderstorm will produce severe weather in the future, up to about 60 to 90 minutes in the future. ProbSevere is a storm-centric product, so meaning the output is relative to storm cells that you can manually identify in radar reflectivity data. And so what we do in AWIPS, how we display this output is via a colored contour that is overlaid on top of radar reflectivity, where the contour indicates, inside the contour is where the automated system identified and is tracking a storm cell. And then in AWIPS 2, you can hover over that storm cell and you can actually get the actual probability value along with all of the NWP, geostationary satellite data, MRMS radar, and ground-based lightning data metrics that went in driving that probability. So most people have seen this, but if you haven't, that's how we relay this information to the forecasters so that they can easily integrate this into their existing procedures, where in severe weather warning operations, of course, you're relying on interrogation of base radar data. So having something that easily integrates with that we deemed critical, and that's how we came up with this display. So just walk you through sort of a typical case. Nothing real special about this, but this is sort of a typical illustration of how ProbSevere works. So we're going to look at a region in the box in the upper Midwest on May 8th in 2014 that was sort of at the edge of a slight region analyzed by SPC. And so we'll just pick it up at 1644 UTC. The type of environment we're dealing with here is modest, CAPE, and good shear. So at 1644 UTC, the probability of severe for this particular storm in southeastern South Dakota is 27%. 2 minutes later, it jumps up to 54%, and that's in response to strong satellite growth rates. So from the satellite metrics, we're looking at how the cloud evolves in time. So how quickly does it develop in the vertical, and how quickly does it glaciate? And so both of those metrics indicated a storm that is consistent with robust convection that would later on produce severe weather. We also had increases in lightning in that 2-minute time period. 2 minutes later at 1648 UTC, probability jumps up to 78%. As the mesh increases, so the maximum expected size of hail is one of the MRMS metrics utilized, and the ground-based lightning, the total lightning in the cloud also, or in the storm, also increased. We fast forward about 40 minutes later, and the probability is 85%, and that's when the severe weather warning was issued for this cell, and then 6 minutes after the warning, golf ball-sized hail was reported. So this is sort of the idea where ProbSevere gives early insight into which storms you need to pay the most attention to. So in busy scenarios or in difficult to, in sort of marginal, difficult to analyze scenarios, that's where it really helps. I want to show what the impact of satellite is. So, this does have, we do utilize radar data, which you might imagine has a big impact on the final probability, and of course it does. But the satellite part does matter. And so what we did for this case is we ran an experiment where we removed GOES data and we ran with everything else and compared that to the full-blown ProbSevere that included the GOES data. And you could see what the probabilities were as a function of time with and without GOES. So when the probability with the GOES data at 1646 hit 54%, without GOES it was about half that. And then the probabilities increased more slowly with time without the GOES. So in other words, you lose your lead time. And so that's where the satellite part really offers the best information. And this is with the old GOES constellation. With the GOES-R constellation, GOES 16 and then eventually GOES 17, we're expecting the impact of the satellite to increase. So just how does this relate to big data? So each ProbSevere input-output file, which we get output at the MRMS time resolution. So every 2 minutes we get an output file. Because this is just very simple storm metric information, the size of an output file is on the order of kilobytes. So each hour, right now, we ingest about 1.3 gigabytes of input data, but the total output does not exceed about 6 megabytes. So we're really distilling the large data volumes into relevant, actionable information. And that's what the current GOES constellation. When we add in one from the GOES-R series, so we add in GOES 16, the hourly input jumps up to 10 gigabytes, but the output file size still stays the same. So even though the quality of the output will improve with the new GOES-R series, but the size of the output does not increase. And then we add in another GOES when we get GOES 17, and it jumps up to 19 gigabytes an hour. Again, the output doesn't, file size doesn't change. And then if we were to go from the rapid refresh to the HER with 2 GOES, then we're up over 22 gigabytes per hour. So you get the idea here that this is an important concept, distilling all of this data into something that it more directly speaks to the operational decision making. Okay, so we've done a lot of verification against local storm reports. So this is ProbSevere verification versus NWS warnings using a probability threshold from ProbSevere of 60%. So a lot of you may have seen this plot, but the orange bars are the ProbSevere model, the blue bars are NWS, and what we have here relative to the y-axis on the left is probability detection, false alarm rate, and critical success index. On the far right, we have median lead time to the first report of severe weather, and that's relative to the y-axis on the right. So what you can see, of course, NWS is more skilled than a computer model. As I said at the beginning, I don't think big data methods are going to be taking over for humans anytime soon, certainly not in my lifetime. And so, this analysis bears that out. The humans still outperform the computer by a fair bit, but the computer algorithm is still skilled enough to be quite useful. But where you really gain with this big data method is in the median lead time. So 33 minutes for ProbSevere relative to 19 minutes. So that's a jump up of 14 minutes. Our latency on this product is about 3 minutes. So you subtract that out, and what you get is about an 11-minute lead time jump relative to the first report of severe weather for all hazards. We've also done ProbSevere reliability as a function of the CAPE and the shear, so the buoyancy and the shear. So how does it perform in different environments? So what you want is the red line, which is ProbSevere probabilities as a function of the actual frequency of occurrence of severe weather. You want that to line up on the blue line. Then your model is perfectly calibrated. So it means when we have a probability of 50%, that means that a severe event was actually observed 50% of the time. So the model would be well calibrated. So what we see, that overall the model is well calibrated throughout most of these convective regimes, with the exception of when we have low shear, higher CAPE environments, we tend to overestimate the probability, ProbSevere. And we've made some new developments that I'll talk about later that I think has helped address that issue. But the ProbSevere that people are getting in their WFOs now through our experimental feed does exhibit this behavior. We've also done verification on a WFO by WFO basis. So we have this interactive map you can go to online. You see the URL there, where you can hover over or click on the WFO region, and you can get ProbSevere verification statistics. And you can do this for different probability thresholds, and you can see how it compares to the NWS. So it gives you an idea of what the regional variation and capabilities are. Of course, what we see from this analysis is, the areas where we struggle the most are out west, which you might expect. Also in the northeast, it is proven difficult, and the far southeast, Florida in particular. But the other regions, the skill is quite reasonable. We also have an ability to go back and look at how ProbSevere performed on a given day in sort of a bulk manner. So we have these daily storm tracks that are derived from the ProbSevere model, because we're tracking storms in time. So you can actually go to our website, you could plot up these storm tracks for a day, and then you could hover over them, and you can actually get the ProbSevere probability at a given time along a storm track. And then on top of that, you can overlay the SPC local storm reports, and you could hover over those and get more information on time and what the actual report of severe weather was. Then on top of that, you can overlay the warning polygons, severe thunderstorm and tornado warning polygons, and you could see how all of this played out relative to one another. So what were the probabilities before a polygon was issued? What was it during? What was it after? When did the reports of severe weather come in? So this is a nice way to get a snapshot as to how the model performed, particularly on busy days when it's hard to otherwise get that assessment. We've had ProbSevere in the hazardous weather test bed for the last 3 years, and we're now doing our 4th year. And there's a lot of different blog entries here that where forecasters they write up what they thought was good, what they thought needed improvement, and we've benefited from that feedback a great deal. That feedback has very much filled into or influenced our development efforts. We ask a bunch of questions of forecasters at HWT. One of the questions we ask every year is, would you use ProbSevere model during warning operations if it was available in your WFO? Of course, it is available in WFOs now, but initially it was not, and almost always we get a 95+% response that yes, they would. Given that it is, forecasters have a very difficult job. We have a great appreciation for that, and we know that it's very hard to come up with tools that are sort of universally accepted as making the job at least a little bit easier. So we thought that this was a positive response. We're also providing support to the probabilistic hazard information experiment going on in the hazardous weather test bed, where this is part of the FACETS program, looking at trying to make probabilistic warning swaps. And so right now the FEE experiment is going on, and ProbSevere is part of that to help initialize these probability swaps. We had a more formal evaluation at the WFO level in 2016 with the Central and Eastern regions. Chad Gravel, satellite liaison at the Aviation Weather Center, led this, where we had 15 weather forecast offices from the Eastern region and 37 from the Central region participate. So, we potentially had 900+ sets of eyes, forecaster eyes on this. So this was a really good thing. We got a lot of feedback. Good constructive criticism, but we also got a lot of positive feedback. And so, one of the questions we asked forecasters who participated in this was, how useful did your office find ProbSevere for providing confidence in issuing or not issuing convective warnings on thunderstorms, and it's on a scale of 1 to 10, where 10 is extremely useful. And the general response was quite positive. We are in the upper range of that scale, where 62 forecasters responded, and the median in mode response was 7. We asked the same question of SUs, and the response, and 25 of them responded, and again, we were in very much the upper range of that. Forecasters and SUs have sort of taken it upon themselves to develop tools that can interact with ProbSevere, and one of them is this time series tool that Tom Holquist from he's the SU in Minneapolis, St. Paul. He made this web-based tool where you can put in a ProbSevere storm ID, and it will plot up a time series of the various metrics. So you can go and look at this. And so this got us thinking, well, forecasters find this useful, so we're now thinking about ways we can implement this capability within AWIPS, leveraging existing AWIPS capabilities. So I do want to say that I think ProbSevere is a good example of multi-NOAA line office collaboration, both in the research sense and the R2O sense. So ProbSevere relies heavily on the MRMS, which was, of course, was developed at OAR in NSSL in collaboration with their university partners. And we've had tremendous collaboration with the group in Norman on ProbSevere. The National Weather Service, as we've had this in the hazardous weather test bed and WFOs. We've had really good scientific discussion with users on the type of development we should be looking at doing. We've benefited greatly from that. And of course, in NESDIS, we led the development of this. So in research, this was a very good cross-line office collaboration. As we're now looking to transition this to NWS operations, it's also, that collaboration is extending to that effort. So we have NWS shepherding and the effort to try to get this as an approved project to get into operations, and they'll lead, if that's successful, they'll lead the effort to get this in. We're going to integrate this with the MRMS. That's the plan, and of course so that means we're working closely with OAR, and we're the keepers of the ProbSevere code. So again, this cross-line office work to get this in operation. But we're not done with the development either. We think this is sort of just the tip of the iceberg of what we can do, and there's additional NWP type data sets that we can look into using. Recently, we've been thinking a lot about how we might incorporate the SPC optimal analysis, which at times is can be superior to, in regards to certain metrics at least, to the rapid refresh. We of course have on orbit GOES 16 now, so we're working on how retraining the model so that it's optimal for on orbit GOES 16 data. Plus, we now have a geostationary lightning detection capability, which is brand new. It's a brand new measurement capability that we have to learn how to work with and incorporate. There's additional MRMS products we can look at using, etc. So we've sort of taken all of this and we started to move the development in the direction of hazard-specific probabilities. And we did this based off of NWS feedback. So we now have a version of ProbSevere that's being evaluated in the 2017 HWT, where we actually do individual probabilities of hazards. So probability of tornado, probability of hail, probability of wind. And then we could aggregate those probabilities to still get the overall probability of severe. And so that's what I'll go through now, give you some insight and a little bit of a preview of some of the latest developments that are going to be evaluated at HWT this year. So the first one, probability of tornado, or ProbTor. And so what we've done here, it's the same general concept, but we're using different metrics in the model. So we use the azimuthal shear in both low and mid levels from the MRMS. We have flash density from the Earth networks. And then from the rapid refresh, we have a slew of metrics that speak to the kinematic and thermodynamic environment in which the storms are forming. And all of this comes out to give you the probability of tornado. And so just an example of the type of benefit that we're kind of excited about. We have a lot more work to do, but we think this shows promise. In February, there was a rare severe weather outbreak in Pennsylvania and New York. And there was actually an EF2 tornado that had a fairly decent path that went from Luzerne to Lackawanna counties in northeastern Pennsylvania. And so, looking at this with ProbTor, we had very high probabilities of tornado, 91% to be exact, about 10 minutes prior to the warning and about 23 minutes prior to the formation of the EF2 tornado. So the idea here, again, is to make severe weather warning operations more efficient and also perhaps help add lead time and ideally accuracy to severe weather warnings, where is the ultimate goal. So we have done preliminary evaluation of ProbTor. And so this is a similar diagram I showed for the overall ProbSevere evaluation, where POD, FAR, CSI of ProbSevere or ProbTornado relative to NWS. And then we have the median lead time analysis to the first report of tornado. And doing this at the 60% probability threshold, what you see is that, our probability of detection is far less than the NWS, but the FAR is comparable, and the CSI is less, as we would expect, because our probability of detection is less. The median lead time, though, is about 10 minutes longer than the NWS warnings. Now, just to clarify, this is a storm-centric verification, not a polygon-centric verification, because ProbSevere produces storm-centric guidance. We're not issuing polygons. And so basically what we did is we took the, when we were evaluating the NWS on this, we didn't care if the first tornado report occurred in the first warning polygon issued for a given storm, or the second or the third, or so on and so forth. It didn't matter to us. Just as long as that storm went on to produce a tornado, it was counted as a hit. Because that's how we grade ProbSevere, because we don't have polygons to grade against. So that's why the lead times here are larger than what you have in your official database, which you score a little bit differently. But it is an apples-to-apples comparison when we're comparing ProbSevere to the NWS here. We've also looked to see how well calibrated ProbSevere is, again, for tornadoes. And we see it's pretty well calibrated. If anything, we have a tendency to underestimate the probability over much of the probability range. The red curve being above the blue line means we're underestimating the probability. That being said, despite the promise, there are some known issues that we have to work. There are radar artifacts. Utilizing the velocity fields, they are noisier. There's also these false rotational signatures that you occasionally get that even through manual interrogation of base radar data are difficult to diagnose in real time. So those are going to trip up Prob Tornado as well. There are limitations with some of the RAP metrics, particularly the low-level helicity. That's where the optimal analysis from SPC, we think, would add a lot of benefit, but we have to figure out how we get that in a timely manner. Bottom line, though, is I'll reiterate, human experts are always going to add value, period. It's a difficult problem. We've also gone ahead with it. So we have an all-hazards version of ProbSevere experimentally now within HWT. So not just ProbTor, but we have ProbWind, ProbHail as well. And I'll just show, this case from April 6, 2017 in the Washington, D.C. area, how the all-hazards ProbSevere compares to the legacy version, what I'll call the legacy version that you've become accustomed to. So in this legacy version, ProbSevere struggled with wind events. Things that weren't going to produce a large hail, ProbSevere tended to struggle with a bit. And so this was one of those events where the probability of severe at this given time, where there were multiple warnings on this storm already and it was producing severe weather, were only 12%. But if you go to the all-hazards version of ProbSevere, you can see we had 13, 80, and 14% probabilities of hail, wind, and tornado, respectively. So the overall probability here, which we take as the maximum of those three, we showed it's actually pretty well calibrated if we take the maximum, is 80% compared to 12. And the all-hazards version kind of nails this wind threat, overall wind threat being the main thing. This is the verification of the all-hazards ProbSevere with respect to the first severe storm report. So, this is actually the legacy ProbSevere verification. And what I'll do is I'll flip to what the all-hazards ProbSevere verification is. So here's legacy. Here's the all-hazards. So look at the CSI bar, the orange CSI bar. You'll see that the all-hazard nudges that up a bit. So it nudges it up by reducing the false alarm rate, primarily. Whereas the median lead time to the first report really doesn't change very much. But the overall skill goes up. So we think that's progress. So just to summarize before we go to the discussion here, so our goal, and the goal of ProbSevere, it's designed to directly support NWS severe weather warning operations through, distilling these large multi-source data sets into actionable information. In terms of R2O, we have increasing optimism that ProbSevere, that we'll find a path to operations for it in the future. User readiness, we have an indication that most NWS forecasters have taken the ProbSevere training and have experience using it within either HWT or within their WFO. Every WFO in the lower 48 now, through the regions, has access to ProbSevere in their AWIPs in near real time, because ProbSevere was baselined in terms of its display capability in AWIPs quite some time ago in version 14.4. In terms of development, we've developed an all-hazards version of ProbSevere that is currently being evaluated in the HWP experiment and will be evaluated in the experimental warning program of the HWT which starts in June. And the future availability of that in baseline AWIPS, I mean, it depends on how it does in HWT and what the AWIPS development and rollout schedule is. So we don't want to put anything into core AWIPS until it's gone through a test bed like HWT and has been proven as a reliable tool. That being said, it is available online, so forecasters that are curious can look at it on our website, or we can point you to place files that you can view within the GR2 analyst tool. But we're not recommending you use it for operational decision making. It's just more, if you're curious, you want to look, we're happy to take early feedback in a very informal way, but again, it's going through HWT review right now. Right now, ProbSevere is still run with the legacy GOES system, so GOES 13 and GOES 15. We're in the process of retraining it using on-orbit GOES 16 data. Because it is a statistical approach, it does need to be retrained with actual on-orbit data. We expect that to be done sometime in the fall of 2017. And we're optimistic we're going to see improvements in lead time and accuracy just because the GOES-R capabilities are so much better than the legacy GOES system in terms of spatial, spectral, and temporal capabilities, plus we have the on-orbit lightning measurement capability. There are additional resources here, so you have access to this presentation, so you can check out those links if you're interested. There are papers, and with that, ready for questions and discussion.
Okay, thanks, Mike. Really appreciate you plowing forward so we get to the Q&A. So those of you online, if you would use the raise your hand feature, if you would like to ask a question, Mike, please do so, or use the chat feature. I'm going to use the host prerogative to ask the first question. Could you, Mike, just take a moment to describe the statistical model that you're employing to come up with the probabilities? Mike, did we lose
Sorry,
Mike?
I was on mute. Yeah, it's a naive Bayesian model. The naive part comes from the fact that there's an assumption made that every predictor in the model is independent of the other, which of course is not true. Despite that, though, naive Bayesian classifiers have been shown to be rather reliable, despite the independence assumption being violated. So it's a common way to bring together multiple predictors where if you try to do it in a straight away Bayesian model where you had all the predictors be a function of the other predictor, the curse of dimensionality kills you. And so you can't implement it from a practical standpoint. So that's why the naive assumption, which has been demonstrated for like statistical models and hurricane intensity forecasting and things like that, we adopted it here. Of course, there's other ways to do this. You know, random forests, looking forward in the future, have shown a great deal of promise for this type of data integration and something we may look at in the future in research. But for right now, it is a naive Bayesian classifier.
Okay, thanks. And just as a quick follow-up, so when you do these sensitivity studies where you sort of exclude GOES data, how long does it take to rerun the probabilities for that sort of thing?
As long as we have all the data, we have that pretty streamlined. It's not too hard for us to do. So we can do. We've done bulk analyses on this where we run through a lot of cases and looked at the verification statistics. What we see is when we look at this in a more of a statistical sense, is that the accuracy or the skill of the model doesn't change that much when we take out satellite data. It decreases a little bit, but what really changes is the median lead time. We lose a lot of our lead time when we take out the satellite. And so as part of our GOES 16 work, we're going to do a really in-depth analysis of the impact of satellite, including assessing what are the impacts of going to GOES 16 data from the legacy GOES system, so that we can really quantify how these new observations, which are very expensive, and how they're really benefiting this part of operations. We think that's a critical analysis to do.
Okay, I lied, Mike. I got one more. So when you're running the Bayesian model, I mean, how much data are you plowing through? We're talking about years. I mean, it sounds like a large amount of radar, satellite, storm reports. What does that look like?
It tends to encompass sampling throughout a given year. So we don't do every day of the year, but we do sampling. We have nearly every month of the year represented in our training data set so that we can get at cold season, convection, and things like that. So, you know, how many days it adds up to, I don't know off the top of my head, but it's probably, I'm looking at 100 days or so spread out throughout the course of the year.
Okay, thank you. Let's, John.
Storms.
Thousands of storms. Okay, great. John, do we have a question?
Sure. Yes, we do. Looks like Keith Mayer, Billings, WFO, says, last summer during our monsoon, we noticed that ProbSevere was drastically overblown for warmer type regimes, like we see in August and early September. Has there been any updates to improve this type of error?
Yeah. So what in the all hazards version of ProbSevere, we've reduced that false alarm rate a great deal. So when I flip through slides 34 and 35, when you go from the legacy, so what you were looking at last summer, to the all hazards version of ProbSevere, which is not yet in your AWIPs, what you see is the false alarm rate bar of ProbSevere goes down by a noticeable amount. And what that is really addressing is the type of false alarms, sort of high CAPE, pulse type environments, like the one that was referenced in regards to the convection in Montana. So I think in the all hazards ProbSevere, I think if that makes it to your AWIPs at some point, you'll see a good improvement there.
Okay, thanks, Mike. Next, John.
Okay, Daniel Melendez has a question, and he says, is the skill computed over the same pixel area as the National Weather Service verification?
The same pixel area. So
yeah, I think he means the warning polygon, I believe.
Right. Yeah. I believe that's pretty much true. Again, we're evaluating storm tracks from ProbSevere, but then we know we actually have undergraduate students. We're stationed here at the university, so we have access to the academic department, the atmospheric sciences department, and we actually have undergraduate students who sit in a very dark room for very long periods of time, manually analyzing storms. And so what we do is they match up storms and radar and with object IDs with ProbSevere, reports of severe weather, and NWS polygons so that we can accurately assign a given warning polygon to the correct ProbSevere storm. So our verification, which is done over many thousands of storms now, is based off of careful manual analysis done by eager graduate students and undergraduates.
Eager, I like that. Okay, thanks, Mike. Next question.
So Daniel goes on to ask further, what was the period of comparison on the WFO scale evaluation?
That was April, May, June, July, and August of 2016, and we're extending that as we go. So that continues to grow. I think we're going to extend it into the fall season, into October shortly. We have that manual analysis done. We just need to regenerate the WFO maps. So if you're thinking about, like, say, convection in the Southwest in the early autumn or something like that, those maps will soon reflect that type of meteorological regime.
Okay, thanks. Do we have any questions in the room? Dennis.
What are your criteria for the various severe categories, and do you have them thresholded such as F1, F2, F3 tornadoes or size of hail?
We don't at this point, but it is something that we're working with or working on doing through this manual analysis. So it's part of the information that we're collecting is the strength of the tornado, so that we can see with ProbTor, for instance, we're very interested in knowing what our probability of detection, false alarm rate, etc., is as a function of the EF level, and we don't have that answer yet, but I can tell you it's in the works, and it just takes time to put together.
As far as your basic warnings, like your threshold for issuing, for saying that you have a warning, is it the same as the National Weather Service criteria?
Yeah, the overall, we judge in terms of overall severe. Yeah, it's the same criteria: 58-mile-per-hour winds, tornado, or 1-inch hail. I don't know if I answered your question, but yeah. Okay.
Follow up, Mike. So you have this. You have to choose the 60% threshold, though, to actually do the evaluation. And how did you arrive at that?
No, you don't have to. I just happen to show it for that threshold because that's around the threshold where it's a good balance between maximizing the skill and lead time. We do the analysis as a function of probability thresholds. We have it done for many more thresholds. But the 60% one is the guidance we gave. If you wanted to turn it into a binary classifier, 60% would be a good balance of maximizing your skill score while having good extended lead time. Because if you go to higher and higher probabilities, your lead time decreases, but your skill score hardly changes. That's what our analysis found.
Got it. Thank you. John, do we have other questions?
I think we do actually now. Let's see. Okay, Steve, I think it's Chiton, would like to know. So could you show the URL for the verification by CWA again?
He's getting to it, but just a reminder, Steve and everyone else on the call, that this whole presentation, the slide deck will be uploaded to the VLab site, so you can go through every slide with all the URLs by accessing that later. But there it is.
Oh.
Okay, I'll leave that up.
Yeah, thanks, Mike. So another question, and this is Steve Smith again. So I've heard, you did a really good job articulating the fire hose problem with more data, and how do we distill that into a product which doesn't swamp the forecasters, even though we're adding more and more data. A question is, I've heard this discussed. I don't know if it's involved in the conversations you have, but the possibility that ProbSevere could be used for the severe warnings in a fairly automated way, so that the forecasters could focus on the more challenging problem, like the tornado. In other words, sort of let the severe go in a, this is into the facets realm, but that problem is easier, I guess, and therefore ProbSevere could kind of help in the semi-automation, so that more challenging problem the forecasters could focus on more in depth. Is that been tried or looked at in either the hazardous weather testbed experiment or any other type of evaluation that you've done so far?
It's been tried in the PHI experiment, so with the facets paradigm. So, they found that the probability for the overall probability severe for initializing the probabilistic hazard information, they found that they didn't have to tweak it very much. They would make small tweaks here and there, so they found it was actually quite decent for initializing those. Now, with the current warning paradigm in a WFO, of course, we'd never recommend that, but one of the main comments that we got back from this WFO evaluation that happened last year was, one of the main utilities of ProbSevere was in busy scenarios, it really helped prioritize where forecasters needed to spend their time. So while not directly being used or automatically issuing warnings, it did quickly highlight which storms they needed to focus on and when they needed to focus on them, thereby improving overall operational efficiency in these busy scenarios. But the fee thing is the closest to actually doing it fully automatically.
Yeah, great. Thanks. John, we have other questions.
Yes, Gregory Patrick said that, let's see, he says that thank you for delivering this fantastic overview and the planned improvements and experimental enhancements. In viewing some of the legacy ProbSevere output, I've noticed some large storm objects, for example, a solid 80-mile long squall line, where we only get a single probability value for this entire line. This object identification limitation may prove problematic for using ProbTor during QLC events, QLCS events, where several storm circulations could be embedded in a single storm object. We get one value ProbTor for a line segment with 3 or 4 storm circulations. Can you please comment on the apparent limitation, and what could possibility be done to overcome this limitation?
Yeah, thanks, Greg, for your question. Yeah, I mean, we totally agree that's an issue, and it's something that we've spent some time thinking about. You'll never have object identification in a fully objective automated sense. There will always be some overgrowing of objects or something that doesn't quite line up with how you would manually analyze it. But with regards to ProbTor, in particular, we've been thinking about solutions to this problem. And one possible solution is that we make sub-objects within the larger object that are solely based off of the radar velocity field, so that we look for the localized maxima in the azimuthal shear within that larger object, and then we create a display capability that can mark within the larger object where the localized regions of maximum azimuthal shear are, so that you would have a better idea within that larger object where the real threats lie with regard to tornadoes. This is certainly something that we think, forecaster feedback and ideas would help us out, but we're thinking about it at least initially in that regard.
Okay, thanks, Mike. But a quick follow-on to that. So, have you looked at dropping the storm-centric paradigm and just go to a fully gridded ProbSevere so that you'd have, basically probabilities everywhere?
We haven't given that a lot of thought because, the concept relies so strongly on tracking storms in time. So, an object-based approach is really the only way to do that. Now, can you take that object-based and tracking approach and somehow make a grid? I think, there's certainly ways to think about that and do that. I think if we're going to do that, we might want to start thinking about, ProbSevere doesn't tell you where the severe weather is going to occur. It just, in a storm-centric sense, says what storms are likely to produce severe weather in the future or likely to be producing it in the present. It doesn't tell you, where in that storm's, life and relative to the geographic location of that storm, where it's going to be. So I can imagine in the future thinking about this where we wouldn't only do storm-centric probabilities, but we would actually come up with sort of a probabilistic type of swath that would take into account which part of the storm is likely to produce severe weather and where is that part of the storm likely to be in the near future through extrapolation of tracking trends in the short term. So thinking big picture, that's a really hard thing to do, but if we're to take a next step looking 5 years down the road or something, I think we can start thinking about it that way. But right now, it's already a challenge just doing what we're doing. But I think it's wise to always look to the future and what might be possible.
Okay, thanks. This is another follow-up. So I'm sure you're familiar with Steve Goodman's, lightning jump work and all of that with the lightning data, ground-based. And so you mentioned now we got the GOES, the GLM, and we still have ground-based networks. Is the lightning treated? Is this lightning jump treated explicitly somehow in your basing approach, or it's just dumped into the lightning in general is dumped in as a potential predictor? How is that handled?
So the lightning information, what we do is we look at the number of strokes per unit area per unit time, and we looked into the lightning jump where you actually take that lightning trend and try to assign a sigma level to it. So how many standard deviations how big of an anomaly it is in terms of number of standard deviations. We've looked at the lightning jump and we found that it was actually slightly less skillful than using the lightning density information, and that's why we went with that. And we've talked at length with the lightning jump researchers at the University of Alabama, Huntsville, Larry Carey's group, as well as researchers at University of Oklahoma, Kristen Coleman and her colleagues about this. And, we're not sure why we found that. It may be because we had a very large database that we were analyzing relative to the database in which the lightning jump algorithm was analyzed on. But this is still a bit of an open question, and we have an open dialogue with the researchers on that. But our statistical analysis with our data set indicated that we were the skill level was slightly better going to a lightning density approach.
Yeah, well, those studies had always, that was a question, right? There were limited data samples, so it's if you may have found the truth. And okay, other questions.
Well, we actually have two questions dealing with sensitivity studies. So one individual wants to know about, have you denied radar data as opposed to you had denied satellite data? And then also the lightning data, have those sensitivity studies been done? Good questions. What do you say, Mike?
Okay, so I'll start with the easy one. We have denied lightning because lightning was added to ProbSevere about 1.5 years ago or so. It was, in last year's HWT was the first lightning-based evaluation. And what we did find was the lightning did increase the skill, and while increasing the lead time by a couple of minutes. So that was, we deemed to be quite a nice positive impact. So if you can increase your skill while still increasing lead time, we deem that to be a good result. Now the radar one, we haven't done a lot of sensitivity analysis with because our object tracking is so dependent on the radar depiction of the storm. We can run it without radar, but honestly, the skill level will come crashing down. I can just tell you that's the result. But we do have a new GOES-R risk reduction project funded by Steve Goodman, and we're doing this in collaboration with researchers at the University of Maryland, where we're trying to develop an analog to ProbSevere that'll work in regions that do not have radar coverage, such as like the offshore areas, where OPC cares a great deal about convection, for instance. And we're also looking at ways to utilize the lightning to mitigate radar beam blockage out west in particular, where there are parts of the west where the radar coverage is just really poor, and as a result, ProbSevere in its current formulation is pretty poor. And so I think we'll make short-term progress on that part. In terms of the offshore version, where the meteorology is different and all of those things, that's a longer term, that's a 3-year effort. So I think in 3 years we'll have something more to say about that, or 2 years from now.
Okay, great. You're unmuting, Daniel?
Yeah, he seems to have a follow-up question.
Daniel, are you on the line? Daniel Melendez, are you there?
Maybe not.
Okay. For the sake of completeness, Mike, so have you denied the storm environment predictors as well?
We haven't taken those completely out, but what we have done is run numerous experiments with different combinations, and that's how we zeroed in on the combinations that we use. But we haven't just taken them out. Main reason for that is, these are non-observational predictors, so the risk of losing those in a real-time sense, like a radar can go down, or a satellite can experience on-orbit problems, or ground-based lightning networks can experience problems. But the NWP stuff, given the amount of backups and stuff, tend to there's a less likelihood of losing them, so we are less motivated to do those experiments.
Well, that's a pragmatic, but seems like there's potential for some very interesting applied research here, particularly with tornado discrimination. So there's speculation, that what is the magic discriminator in tornadic versus not, the storm environment, to the degree we can capture it, or the lightning, or these sorts of things. So have you looked at that with regard to the tornado problem?
Yeah,
as a research question.
Right. Yeah. I mean, we've done a really extensive analysis of different environmental parameters and their impact on ProbTor. So ProbTor evolved. We probably had 20 different versions of it internally that we experimented with, using different environmental predictors with the same observational-based predictors. We found that the environmental predictors that you utilize matter. And the reason we arrived at the set that we arrived at, things like the low-level storm relative helicity, low-level wind speed, the effective bulk shear, the SIN, the mixed-level CAPE, those things, we arrived at those through pretty rigorous statistical analysis. And so it matters a great deal as to which ones you use. Yeah.
Okay, great. We got one last. Anybody? We're near the end.
I guess Dan wants to know, he was referring to the first plot that he showed, were the performance comparisons made at a similar area size?
Oh, were those CONUS-wide, or is that the question? Yeah.
Probably not CONUS-wide, probably the size of the warning box for both.
Right.
Oh, okay.
Trying to get at the basic verification.
Okay,
yeah, I mean,
so go ahead, Mike. No, go ahead.
Yeah, I mean, it was a large number of storms. It was so I think we had thousands of storms from a large number of geographic regions, so different meteorological setups. And then in terms of like I said, the how we derive the ProbSevere verification versus the NWS was done through rigorous manual analysis of storms. So actually going through historical radar data and matching up the this ProbSevere storms to warning polygons and local storm reports. So assigning a local storm report to a given storm sometimes gets messy, and there has to be a judgment call, particularly when there's a lot of storms in the vicinity. But I think overall our database has pretty high quality there.
One last question, Bob Gahn, go ahead.
Well, that's a comment. I believe you said that your method did not tell you where the storm was going to be. So if you're comparing with NWS, which does tell you where the storm is going to be, I'm not sure how you're managing to prepare them in any realistic manner.
Okay.
I think that's what Melendez was trying to get at.
Yeah, I mean, okay, so we're tracking the storms in real time. I mean, so we have tracking of the storms, and so we know which storms, warning polygons are assigned to which storm. And so this is all done manually. So we have a human actually assigning a storm to a storm report and warning polygons. And then that storm has a severe ID. So we have a very robust ability, time-consuming, but robust ability to make sure we're comparing apples to apples here. So I'm not sure I understand the question.
So the framework is to do this, you're actually going to the warning polygons as the aerial extent for the verification. Is that correct?
Right. So yeah, I mean that's a good proxy for it. Yes.
You're assigning your probability. You're assigning the ProbSevere storm-centric probability to a particular warning and to particular storm reports.
That's correct.
Okay. Okay. That makes sense. All right, we're out of time. So I want to thank Mike for a really thought-provoking presentation. As I said, ProbSevere is a hot topic in Weather Service, and we're looking towards FY18, hoping budgets are great and all that stuff. But it's near the top of the list for transitioning to operations, so we really hope to make that happen. This conversation will continue, as will as evaluations and the great work up there at Sims, Wisconsin. A reminder, so John will send out a notification when the recording of this is uploaded to the VLab website, but you can already take a look at the slides now. They're already up there. Coming up in June, we've got a talk, improving understanding and prediction of high-impact weather associated with low-top severe convection in the southeastern U.S. by Keith Sherburne. So that's maybe that's related. I mean, I think ProbSevere wasn't doing all that well in the southeast, so maybe there's information to be gained relatively doing that well. July, we got Forecast Builder Project by Chuck Grieve. In August, precipitation rate estimation on specific attenuation by Stephen Cox. And in September, the Fee Hazard Services Project, Tracy Hansen and Greg Stump, and you heard that mentioned today by Mike. So lots of good stuff, convectant related, coming up in the next, over the spring, summer now and early fall. Hope to see you in June. Thanks again, Mike, and we will, everyone, see you in coming up in June.